So with slope field, or sometimes called a directional field, direction field, are exactly what they say. It's a field of slopes, a field of slopes. Okay. So in order to create a slope field, what do we need to find a slope? Let's ask that question. What is the one thing we need to find a slope at one point? A derivative, right? First derivative, right? That's where differential equations come in. Differential equations are derivative equations, right? So we're going to use a differential equation to create what's called a slope field or a direction field. Okay? They're pretty tame. They're not that bad. Okay? But when you first look at them, they look kind of crazy, but they're not very hard to understand or create. So we're going to create one. So we're going to do the example down here. Okay? So on the diagram, right? Slope fields are easy to spot because they have a bunch of dots on them. Okay. They have a bunch of dots because we need to do something. We need to find slope at every single one of those dots. Okay. So we're going to create a slope field for the differential equation. So here's our derivative equation. That's our derivative equation, right? We're going to create a slope field for that. Okay. Well, what did we do? So like if you have a first derivative, how did we find the slope? What did we do with the first derivative to find slope? How did we use derivative to find slope? What did we do? Mm-hmm. Plug in the values, right? Usually it was the x values. Well, here, what we're going to have on a slope field is we have x and y values, right? Each of these dots represents an x and a y, right? This is the origin, 0, 0, 1, 0, 2, 0, 1, 1, 1, 2, so on and so forth, right? So what we're going to do is we're going to plug in the x and the y to figure out what the slope is at each of those dots. Okay, so let's start with 0, 0. At 0, 0, x is 0 and y is 0, right? So we plug them into our differential equation. Problem is, sometimes you won't have x's and y's. This guy only has a y. So we don't plug in x. We just plug in y. So when you plug in 0, you get 0, right? So the slope at 0, 0 is going to be 0. How do we draw a slope of 0? What's a slope of 0 look like? What does a slope of 0 look like? Straight line, which direction? Because it could be like this. What specifically does a 0 slope look like? Horizontal line, right? Horizontal line. So what we're going to do on the field is draw a little segment of that. Like a little dash. Horizontal because it has a 0 slope. And then you plug in another value. So let's go to the right. 1, 0. Plug it in to our differential equation. Well, again, I have nowhere to plug in x, so it's just y. So when I plug in 0 for y, I get 0 again. Okay? Where else am I going to have the same slope? Without having to do every single dot, let's look for patterns. Where else am I going to have the same exact slope I did on the first 2 points? Anywhere y equals 0, right? So anywhere y equals 0, I'm going to have the same guy. You start to look for, you're not going to do every single dot individually. You start to look for patterns. This is always going to happen when this is that, when this is this, and this is that, right? All right, so let's go up one. Let's go up one. So let's go to here, 0, 1. What is the slope going to be at 0, 1? 2, because I only can plug in 1, right? And I get 2. So a 2 slope means I go up 2 and over 1, right? So we're going to draw a little sketch of that. We're going to draw a little sketch of that. So up 2 over 1, that's what that line kind of looks like, right? So we're going to draw a little sketch of this line here. Just approximate. Let's move over 1. 1, 1. What is the slope going to be at 1, 1? The same, right? 2. So it's going to have the same direction. It's going to look the same. Where else am I going to have a slope of positive 2? Mm-hmm. Where y is equal to 1. Anywhere y is equal to 1, I'm going to have the same slope. Well, that's the second, that's this row right here, right? Okay. Let's go up. 2, 0. Top row. 2, 0. Or sorry, 0, 2. No, not 2, 0. 0, 2. 0, 2 is right here. Okay. What is the slope going to be at 0, 2? 4, right? 4. Now, compared to this slope here, what is it going to look like? Steeper, right? Steeper. So I got to draw a line, a little dash that's steeper. Because when someone looks at it, they got to know, hey, this slope is steeper than the ones below. Okay. Again, anywhere that y equals 1, or sorry, y equals 2 is going to have a slope of 4. All right, so now let's go down. These guys here, negatives. 0, negative 1. What is the slope going to be at 0, negative 1? Negative 2, right? Plug in negative 1 here, we get negative 2. So negative 2 is perpendicular to these guys here. Or not perpendicular, but opposite. That's 1, 1. A little steeper than that. Okay, move over 1. 1, negative 1. It's going to have the same slope. Plug in negative 1, you get negative 2. Anywhere y is equal to negative 1, you're going to have a slope of negative 2. Bottom row dots. 0, negative 2. What slope am I going to have for 0, negative 2? Negative 4, right? So again, has to be steeper than the last one I did. It's just approximate. You're not trying to draw perfect. You're just trying to draw approximate. Hey, what's up? Who's it? Who are you looking for? No, not this one. Okay. And there you go. That's your slope field. You just created a slope field. Okay. So what do we do with slope fields? Well, letter B. Suppose that you know that the point 0, negative 1 is on the particular solution of the differential equation above. By following the slopes, draw the diagram above what you think the particular solution will look like. Okay, so when they give us a point on a slope field, that's where we start. That's our starting point. So we're going to go make a dot there. 0, negative 1. Change the colors. Let's use a blue. Green. So how do you find solutions on a slope field? Well, from that dot, we're going to move to the right, and we're going to move to the left. Which direction are we going to go? We're going to go with the flow. So if I start here, and I want to move to the right, which way is the direction field telling me to go? Can I go this way? Go with the flow. Which way is the direction field telling me to go? Is it telling me to go up? It's telling me to go down, right? At this dot, I have a negative slope. So that means I'm going down. So from here, I am going this direction. Pretty immediately going down. Now, how about the other direction? If I'm going in this direction, which way am I going? Am I going down too? Am I going up? Well, look at where we're going. If I look over here, the slopes are going this way. So that means I have to go this way. And then if I go up, I can't cross this guy because at 0, it flattens out. So you just go with the flow. You go with wherever the guys are taking you. That's what the particular solution is going to look like there. Essentially, we're doing the same thing we did yesterday and the day before. The only difference is it's visual. It's on a graph. This graph, we're going to do this in a second here. We're going to find the particular solution doing what we did with solving. Okay? Note the graph will follow the pattern. Okay? So it's going to follow the pattern. It's following the direction. That's why it's called the directional field sometimes. It follows the pattern. Right? If I was here, I'm not going to go down because that's not following the pattern. I'm not going to go up because here says it flattens out. You're just following the pattern. Okay? Now C, we're going to solve this guy like we did on your homework. We're going to solve this guy like we did on our notes. So how do we solve this guy? How do we solve that guy? What do we need to do first?
Bring all y to the left and all x to the right.
Yep. First thing, everything with a y goes to the left. Everything with an x goes to the right. This should look familiar because you've done this before for the last all week. This is what we've been working on. So dy dx equals 2y. Move everything with an x to the right. Everything with a y to the left. Wait, what am I doing? Oh, no. Just be, nope. 2 dx. I crossed out the dx when I shouldn't have. Okay. Integrate. Okay. This side's pretty easy. It's 2x plus c. What about the other side? What's the other side going to be? Natural log. Natural log of y. Okay. Plug in your points. Plug in the points. So we're plugging in the point 0, -1. 0, -1. That's the point that they said to plug in. So we're plugging in a 0 for x, -1 for y. The natural log of +1. What's the natural log of +1? 0. equals 0 plus c. So c equals 0. Last thing, how do I solve this guy for y?
Put in keys the base, so to speak.
So I'm going to change it, run out of room here. Change it to log base of e of y equals 2x. Change it to an exponent. E to the 2x equals y. And if I go to Desmos or whatever graphing function and I graph that, guess what it's going to look like? That guy right there.
Basically an exponential.
It's going to look like this guy right here. Okay? So it's essentially we're doing the same thing. One is just a graph and one is doing it using algebra, using antiderivatives in algebra. Okay? So slope fields, that's why I put them on the same notes, because they're the same thing. I used to do them separately, but they're the same thing. Slope fields and solving differential equations are the same thing. One is just analytically, and one is on a graph. Okay? Okay. So now let's do this one. I want you to create a slope field for this guy here. This is a differential equation. I want you to create a slope field for that guy right there. You have less dots on this one. You have 12 dots on this one. Look for patterns. Don't do every single dot. See, oh yeah, when y is this, it's always going to be this. When x is this, it's always going to be this. Okay? All right, I plugged in almost all of them. Almost all the x's and the y's I plugged in just because it was notes. If I wasn't doing this for notes, if I was just doing this separately, I probably wouldn't plug in all of these points. I'd probably look for either try to do it in my head or this is work I don't need to see. If you need to do it, do it. But is it work I need to see to grade? No. Okay, because some of these you can do in your head, right? A lot of you probably just plugged in X and Y in your head and did that. Great, right? That's fine. I'm not grading that. That's a Math 1 standard. That's not a calculus standard to plug in things. Okay. But I plugged, this is, like I said, if you can't do it, take the extra 5 minutes and actually do this so you can get all of those plug in X, plug in Y's, and you can figure it out. Okay. But I highly suggest trying to either do it in your head or look for patterns. Hey, every time y is 0, it's going to be undefined. Okay. All of the y's, when y is equals 0, undefined. Or every time that x equals 1, it's going to be 0, unless it's undefined. Okay. These are both 0. These are all undefined. And then the other ones are very similar. Okay. That's the slope field we built. Now they want us to find the particular solution when x is 0 and y is -1 at this point right here. Wait, that's not right, is it? 0, -1. So it would be down here. It's off our graph. So I can't use the slope field for that because I don't know what the slope is at that point. So the only way to find is by using the steps that we used last time. Okay? So just like we did earlier in the week, dy dx equals x minus 1 y squared, right? Get all of your x's on one side, get all of your y's on the other. So I'm going to multiply both sides by y squared, and I'm going to multiply both sides by dx. So I get y squared dy equals x minus 1 dx. Integrate. Y to the third, 1/3 y to the third. X squared 1/2 divided by 2 minus x plus c. Okay. Plug in your point, 0, -1. Okay. So I'm going to plug in 0 for x, -1 for y. So over here I get -1/3 equals 0 minus 0 equals c. Okay, so I'm going to rewrite this. 1/3 y cubed equals 1/2 x squared minus x minus 1/3. Solve for c. Or sorry, solve for y. So multiply both sides by 3. So when I distribute 3, I get 3/2 y x squared minus 3x minus 1. Take the third root. There you go. Again, how do I check my answer? If you were to take the derivative of this, if you were to find derivative of that, using the chain rule, you'd have to use the chain rule to find derivative of it. We did harder stuff than this last semester. If you were to find the derivative of that, you would get that as an answer. That's a way to check your answer. If you have extra time on a test or something and you're like, oh, I want to double check, that's a good idea. Okay. All right. So with slope fields are one of the things that could either be multiple choice or free response questions. I've seen them be free response questions. I've seen, in fact, this example here is a free response question from past years. I took it and put it on here. Okay. Those are the types of free response questions you might have. Okay. Or I've seen them on multiple choice. Do something like this. So if you turn the page over, matching slope fields. Okay. Where they want you to match the slope field, right? So look at this example here. How would we do this example? There's a reason I put this example on here. And if you don't look carefully enough, you're going to miss it. So take a look at it. Take a look at it. To create a slope field, what do we need? We need an equation. What type of equation? Because we have, 8 equations over there? Y equals, y equals, y equals. We have those. Are those okay? Right? We need derivatives, right? And we don't have derivatives. We have y equals, right? So to do a slope field, we need a derivative equation. Okay, we don't have derivatives of this guy. But But what do the slope fields tell us? What does a slope field tell us? What does that guy or that guy tell us?
Slopes at each point.
Okay, slopes at each point, but bigger picture. At each point, it tells us the slope, right? But what does the entire picture tell you? Like, what does the entire picture tell you?
Where the equation's going.
Where what equation's going? You're right. I'll give you a hint. It's written down. Sometimes it helps to read. Even in math class, it helps to read. What does the entire picture tell you? It gives you direction of what? What does it give you direction of? It gives you a solution, right? It gives you direction of a solution. Here's the big question. What is a solution? We just got a solution, right? We just got a solution. There it is right there. That's our solution, right? What does that mean? What does that mean when we say solution? When I say that's a solution, what does that mean? It's the original equation, right? It's the original equation. So a slope field is a roadmap for the original equation, right? This is a roadmap for the original equation using the slopes, right? So now let's go down to this guy here. How do we do this guy? The one right below it's easier because they give you all of the... But this guy here, how do we do this guy? There's an easy way and there's a longer way. There's two ways to do it. One way is the easy way. Take you about 15 seconds to do this problem. And then the other way is a little longer. Take you about 15 minutes to do the problem. Either way will get you the right answer. That's the long way. So one way to do it is to find the first derivative of every single one of those guys, right? Some of them are easy, right? The derivative for A would just be 0. The derivative for B would be 1. The derivative for C would be 2x squared, or 2x, so on and so forth, right? And then what would I do with all those derivatives? What would I do when I find the derivative? These aren't hard. These aren't complicated functions. They're pretty straightforward. What would I do with all of those? Plug in X and plug in Y and see which one to match, right? That you could do that, but that will take some time. It works. I don't want to say it doesn't work. It works. You could do that, but that'll take you about 10-ish minutes, 15 minutes. And let's say this is a multiple choice test. What's a faster way? What's a way that you can do this super, super easy? Go with the flow. Go with the flow. What is this graph doing here? What is the graph number 1? What is that doing? Go with the flow. Looks like that, right? Okay. Which one? That's a solution. Don't I have a bunch of solutions over here? Which solution does it match best? Sine and cosine, right? It matches sine and cosine. What's the difference between sine and cosine? When you're looking at a sine and cosine graph, what's the difference? What's the key difference between them? Where does sine start?
Starts at the origin 0, 0.
Well, they all start at they all start somewhere. But my question is, where does it start? Where do I go? If you're drawing sine graph, it goes up and then comes back down, then goes back up, right? Whereas cosine, first thing it does is go down and then comes back up, right? So let's go here. Which one does it do? Does it go up or slow down? It goes up and then comes back down, right? That's sine. Yep, that's sine. So this guy is going to be y equals sine of x. Number 2. Well, here it flattens out. It kind of flattens out there. The slope is 0. Right? And then here, I kind of drops off like that. And then up here, it kind of picks up and picks up like that. I'm just following going with the flow.
Similar to
And that's cubic, right? And that's a cubic. Y equals 1/3 x cubed. Right? Either way works. I just didn't want to take up time doing finding derivatives of all those. But like I said, if you need to, find derivatives of all of them and then plug in points and see if it works. That'll work. Okay, it's not the most efficient way, but hey, if it gets you the answer, that's all that matters. Okay? All right, so what I want you guys to do is so the last 10 or so minutes, I want you guys to work on this. Okay? Each one has one match. A, B, C, all the way to F has one match. Doesn't match twice, only matches once. Okay? So I want you to match them with the differential equations. Okay?